then back, and then back, and then back, and then back. You see? So that's why the potential energy is so important in describing what happens to an object. And the other way to answer it again is imagine the derivative right here. The derivative is negative now, right? The derivative of this is negative, and then if the force is the negative of the negative, the force it feels is positive. So over there it feels a positive force which pushes it this way. Okay, how about if the object is placed at x equals 4? What happens to the object? Yeah, exactly. Imagine what would happen to a ball that is on the bottom of a valley. It wouldn't move at all, right? So it should just stay there. The official way to say that is whenever the potential energy has a local min, then the object is at equilibrium. You see? So when U has local min, object is in equilibrium. When U has local min, object is in equilibrium. The reason why is because when you take the derivative, right? When the object is here, you take the derivative. Well, the derivative of that point is 0, right? So therefore, when you place an object in the local min of the potential energy function, it feels no force. And therefore, when the force is 0, the object stays there. Now, a lot of times they will also want to ask you, is it a stable equilibrium or an unstable equilibrium? Okay, here's what they mean by that. If the object is placed at 3.8, will it tend to move towards the 4 or will it tend to move the other way away from the 4? That's how you can answer if it's stable or unstable. Okay, so if you place it at 3.8, and then is it stable or unstable? It goes back towards that, so it is stable, right? If it goes back to the equilibrium point and oscillates around that equilibrium point, it is stable. So, therefore, when potential energy has a local min, it gives you stable equilibrium. How about when the potential energy has a local max, let's say at the point 2? If I place the object there, what happens? At x equals 2, the force is again 0, right? So when potential energy has a local max, F, which is negative the derivative, is 0. Okay. Therefore, it's again equilibrium. So, object feels no force and is in equilibrium. However, this time, it's unstable equilibrium. Why is that? Because you have unstable equilibrium because you've got to imagine what would happen to an object which was placed at 1.8 or 2.2. Okay? What would happen? if x was 1.8 or 2.2. Well, imagine what would happen to a ball placed here or here. It would roll down the hill, right? And the other way to visualize that is when the derivative of this is positive, the force is negative, and the derivative of this is negative, the force is positive. So if it's placed at, let me erase some of these older ones. If it's placed at 1.8, right here, the derivative is positive, it's going to feel a negative force. So if it's placed right there, it's going to feel a negative force. And if it's placed right there, the derivative is negative, it's going to feel a positive force. It's going to go that way. Well, if it's placed here this way, if it's placed here that way, so therefore it's an unstable equilibrium. It doesn't go towards that equilibrium, right? So unstable equilibrium. So the easy way to remember it is local max gives you unstable, local min gives you stable, and that's about it. So let's do one example there with a certain case I'll give you here.